Yuki, Shirai, go ahead and take it away.
Hi, good afternoon, everyone. Today, I'm Yuki Shirai, and today I would like to talk about our latest work, robust manipulation, specifically robust pivoting, as you can see in these teaser videos. Okay, so let's consider the task of assembling a gearbox. In this task, the robot might be presented with the objects, which are too big to grasp, so the traditional two-finger gripper might not be able to grasp it. Similarly, in this case, the peg is in a desired pose, so robot may not be able to insert it. So to overcome these issues, robot must have the capabilities to deal with these objects to realize successful assembly system. So in this work, we propose that modular assembly system where robot first reorient parts using external contacts, and then robot can successfully perform the desired task. So there have been several notable works in dexterous manipulation which consider stable pivoting. However, I would say all of those works consider sticking contact where the object is always in the grasp of the robot, and thus inherently stable. More formally, it means that reaction force needs to be within the friction cone, so robot can easily increase the reaction forces to stabilize the manipulation. In contrast, in this work, we assume stable pivoting where robot needs to ensure slipping contact at external contacts, which is more difficult to control because you need to let reaction forces on the edge of friction cone. Another challenge arises from uncertainty. In general, robot might not know physical parameters beforehand, such as mass or COM location, which could lead to instability. For example, in this video, the weight of the gear was much heavier than what we had estimated, so robot lost the contact. Similarly, in this case, the weight of the object is much lighter than what we estimated, and again, the object is in the air and lost the contact, and mission failed. So what I would like to mention here is that robustifying controller is very important, but unfortunately, we cannot use the traditional robust optimization technique here directly, since there's no control input to you to satisfy all the uncertainty realization. Furthermore, in practice, we observe that adjusting fingertip position is very useful during pivoting manipulation, but it will provide, to reason this, we need to consider complementarity constraints such as sticking, slipping between the object and the manipulator, like here. Okay. So based on those research challenges, here I would like to clarify our problem statement. So in this work, we work on pivoting in 2D from pose A to B with 2 external contacts and 1 contact from a manipulator. And we aim at designing robust controller, which is robust under uncertain physical parameters such as mass or COM center of mass location, COM. And we can easily formulate trajectory optimization problem to solve this problem. For example, you can consider kinematics, quasi-static constraints. In this case, we are considering slipping at external contacts, so actually friction cone constraints becomes equality constraints. Also, as I mentioned in the previous slide, we also have sticking, slipping constraint, which is handled in complementarity constraints. And we can easily get, by solving this optimization problem, we can get controller, but in practice, what we observed in hardware experiment was that the controller showed very poor performance because this trajectory optimization problem does not take into account uncertainty or robustness. So with these challenges, motivations here in this work, we analyze frictional stability margin under physical parameters, under uncertain physical parameters such as mass, COM location. And based on that analysis understanding, we formulate contact implicit optimization using Bilevel optimization to obtain robust open loop controller. And then we verify its robustness in hardware experiments. So the key insight in this work is that friction can compensate for uncertainty. In this case, let's consider the case where the uncertainty exists in mass. So in this example, the weight of the box is lighter than what we estimated, so friction forces can adjust from the nominal to maintain static equilibrium. Similarly, in this case, the weight of the box is heavier than what we estimated, and again, friction forces can adjust from the nominal to allow the stability of the object. we define largest stability margin that friction can compensate for during a contact of configuration of object with external contacts as frictional stability margin. And this we can get time history with the stability margin. And by using, here I would like to emphasize that, this stability margin, we can predict the worst case stability over the entire trajectory, and we can maximize it so that we can obtain robust open loop controller. And here I would like to emphasize that we improve the worst case stability margin. So actually, time history of the margin would be updated. So for example, in this case, before I run open loop controller optimization, we observe the worst case stability margin at t equal 1. But thanks to controller now, yes, worst stability margin at t equal 1 is not the worst anymore, but instead now we observe the very worst stability margin at t equal 0. So what I'm trying to say here is that stability margin in this work is implicitly defined. It is the function of trajectory, or I would say controller. And in this work, we use linear programming to get the bound of the stability margin, or you can imagine bound of the safety set. And by using this updated time history of the stability margin, we can solve optimization again, and eventually we can get optimal open loop controller. Yes, we are working on nonlinear programming, or I would say non-convex NLP. So either way, our obtained controller is locally optimal. So here I would like to focus on discussing more safety region. So let's say this blue circle represents safety region. Within this region, object is stable or maintain static equilibrium. But let's say here somehow we obtain locally optimal safe region, or not globally optimal safe region. And we can still run optimization problem and get the open loop controller over this safety margin, not globally optimal safety margin. And we can expand it. But what does it mean physically? I would say it doesn't mean so much, I would say, because the controller will stabilize the object which is already stable. It's not interesting, at least to me. I think what we are interested in that we want to have the open loop controller which is robust, which can stabilize the object which is unstable without the controller. And to realize that, we need to have the exact globally optimal safe region. And if we just iteratively solve two optimization problems based on the previous slide, there's no guarantee that we can get the locally optimal controller over the globally optimal safe region. And to avoid this, we formulate Bilevel optimization problem, where we define lower level optimization problem for finding time history of the stability margin, and upper level optimization problem for finding optimal controller to improve the worst case stability margin. We use KKT condition to combat this bilevel optimization problem into one single nonlinear programming problem with many complementarity constraints. Here I would like to emphasize two things. One, first thing is that by using KKT condition, now we can have the access to gradient of the lower level optimization problem, so we can utilize off-the-shelf solvers such as SNOpt, IPOpt to solve this bilinear trajectory optimization problem. Secondly, we intentionally designed the lower level optimization problem as LP. We can get globally optimal safety region because KKT is sufficient and necessary condition to give you globally optimal condition for complex optimization. So yeah, so far I discussed our method, and here I would like to show some results. So first, I would like to show time history of the stability margin we obtain from our trajectory optimization problem and benchmark optimization problem, which does not discuss any robustness. So here, I want to say, so each figure consists of two trajectories. Each trajectory has two trajectories. One is representing the time stability margin along the positive x-axis, and the other one representing the stability margin along the negative axis in this tiny figure. So yeah, in this case, we assume that uncertainty arises from COM location. And this pink line represents the stability margin 0. So what I'm trying to say here is that the further the trajectory is from this pink line, the more stable the object is. And for both methods based on our Bilevel optimization, we observe the smallest stability margin at t equals 0 and 25 seconds. And this table actually summarizes numerical value. The greater the value is, the more stable the object is. And we observe that our open loop controller could successfully design the trajectory which maximizes the worst case stability margin over the entire trajectory with uncertain COM location. Another experiment we did was to see how much robustness we can observe in hardware experiments. So in this work, in this experiment, we intentionally use the incorrect physical parameters mass as an input of trajectory optimization. And we implemented that trajectory in the object with known mass. So what I'm trying to say here is that if this TO optimization is really robust, we should be still able to realize pivoting, even with incorrect parameter. And we actually observe that our controller achieve higher success rate given incorrect parameters. Yeah, and from now, I would like to show some trajectories using our, obtained by our optimization problem. So this is a trajectory obtained from our variable optimization problem and benchmark optimization problem. Almost similar, but I would like to say our trajectory optimization generates more robust trajectory since it realizes larger reaction forces at external contacts to avoid the loss of the contact. And we verify its robustness in hardware experiments, as you can see here. We demonstrate our optimization for different gear. Now we observe that using our proposed method, we actually change the fingertip position. This is done because we consider complementarity constraint sticking slipping, which provide additional robustness. And you can see again, our open loop controller could realize robust pivoting for this specific gear. Yeah, and we also, to show how general our controller is, we also demonstrate our open loop controller for relatively complicated objects such as this peg and more complicated peg, I would say, for this black peg. And again, we could observe successful pivoting. Yeah, so as a summary, we believe that our method makes a first step to realize robust manipulation, especially for assembly task. So using our method, we believe that robot can first reorient parts using external contacts and then realize the desired tasks such as grasping. Finally, I would like to go over some future works. Yeah, first, in this work, we assume point contact, but it will be interesting if we consider patch contacts, because in practice, we observe that patch contact to realize more stable pivoting behavior. So it will be interesting. Second, in this work, we assume that uncertainty only arises either COM or mass. It will be interesting if we also extend this work to consider the uncertainty from, let's say, coefficient of friction, but that will introduce stochastic complementarity constraint discussion, which is not studied so much well. Finally, yes, in this work, we done open loop controller. We implement our trajectory optimization in open loop fashion, but it will be interesting if we, expand this work for feedback control fashion, which will require more extensive work for estimation and control. And yeah, that's it. Thank you so much.
Great, we have time for one quick question, and I'll ask Francesca Negreo to start coming up.
Thank you for your talk. This is Kevin Lynch. So I'm curious about the controller. Is it just a motion controller? You plan a trajectory and then you follow it?
So in this work, we actually force controller, atomic mass controller, I would say, at the end effector, and we have 6-axis FT sensor at the wrist. So we actually track force project given by optimization.
Okay, so then in one sense, is it an open loop controller?
Yeah, open loop control means, so when I say open, So when I say open loop controller means, I would say we are not running something like MPC. We are not deep running trajectory, or we are not having the access to the feedback of the state. We still control force, but we do not control state X, Y, theta in this case. Because to do that, we need to have the access to sensor information such as vision. We do not use vision or tactile sensors. We only use force controller to track force. So yeah, in terms of the force, yes, we are tracking force. That one is closed loop, but pose is not open. It's not closed loop.
Okay, great. Thank you so much.